All right, the biggest, baddest collisions we're going to tackle are elastic collisions. Elastic is a word we used when we talked about waves and sound, when we talked about vibrations. In physics, the word elastic means the object snaps back or pops back to its original shape. In a collision, what that means is these two objects are going to bonk together, they snap back to their original shape, which means that no energy was lost due to the denting. When we talked about impulse, the whole point of crumple zones and airbags in cars is denting by design. Denting absorbs the energy. If we can absorb the energy over a longer period of time, that decreases the force. In an elastic collision, since there's no denting, no energy gets absorbed that way. In elastic, we're also going to say that they don't warm up, so there's no heat created. So a squash ball that gets warm after you play, that wouldn't be an elastic situation. Pool balls, things that don't really get warm after they bonk into each other, those are sort of standard elastic collision things. And this one, as you read it through, you can see I'm calling it a head-on elastic collision. That's physics talk for that it's one-dimensional. If it was a glancing collision, then we've got to deal with components, and especially in elastic collisions, the math gets crazy. I don't want to say complicated, but involved. A lot of, basically it turns into three equations. One of them is quadratic, the other two aren't. The math gets ugly if we're doing a glancing collision in the elastic style. As always, I'm going to doodle a little diagram. I'm going to predict which way I think the things are going after the collision, and then we're going to work through our math. If we guess our directions wrong, the math will tell us as we work through, so it's not critical that we get it exactly right in our diagram. For this one, we've got a 150 going 4 straight south, and a 100 going 5 north. I'm going to leave them in grams. If I convert them to kilograms, it just adds decimal places. Once I start doing the math, I'm going to simplify by dividing numbers anyway, so whether I'm cleaning up decimal places or cleaning up big numbers, we should agree when we get to sort of our simplified conservation of momentum equation, whether in grams or kilograms, as long as we're consistent, we'll agree when we get to sort of the final equations. After the collision, I don't know how fast, but I think the 150 is going to bounce backward. I'm going to call it A, so that's my VA prime, and I don't know that. After the collision, the 100, I think is going to bounce south, and again, I don't know that. I'm going to call it VB. It's one-dimensional, so I don't have to worry about components. I'm just going to set up conservation of momentum. I always start with conservation of momentum. No matter what kind of collision, start with conservation of momentum. If you can't solve it, then double check if the collision's elastic or not. If it is elastic, then you can add conservation of kinetic energy. Conservation of momentum, we've got two objects that started separate and stayed separate, so it looks like that. If I plug in my numbers, again, I'm leaving them in in grams, no point in converting them. I've got 150 times 4. 100 times 5, but the 5 was in the opposite direction, so that flips to negative, equals 150 times I don't know, plus 100 times the other I don't know. If I clean that all up, I got a 600 and a 500 subtraction, so on the left I end up with a 100 equals 150, I don't know, plus 100, I don't know. If you had done the question in kilograms, you would have got 0.1 equals 0.15 and 0.1. The next step I'm going to do is to clean it up. I'm going to have to isolate for one of the variables. When I look at this, my 3 coefficients are all divisible by 50. So I would do that in my head, divide everything by 50. I get 2 equals 3, I don't know, plus 2, I don't know. If you had left it in kilograms, you would still get that 2 and 3 and 2. Instead of dividing by 50, you might be like multiplying to clear decimals. That's as far as we can go with momentum. Knowing what's coming next, I'm going to do one more line. I'm going to flip-flop and get VB all by itself. We could get VA just looking. I'd rather divide by 2 to get VB by itself than divide by 3 to get VA by itself. But it doesn't really matter. When we crank out the algebra, we'll agree on however we do the math. VB all by itself is 1. Once I do the 2 divided by 2, then subtract 3 over 2 multiplied by VA prime. I'm going to call that equation 1. That's as far as we can go with momentum. We can't solve it. We can get that far. Now we're going to invoke the fact that it's elastic. In an elastic collision, since no energy is lost, whatever kinetic energy was in the system to begin with remains in the system as kinetic energy to end with. So it's almost like a conservation of kinetic energy applies when it's an elastic collision. Kinetic energy is always 1/2 mv squared, so I'm going to write it out that way. And once I've got it written out, I'm going to cancel out the halves. But for completeness, I'm always going to write it with the halves, because that's what kinetic energy is. So it kind of looks like my momentum, but it's got an mv squared in it. All right, so there's my conservation of kinetic energy. All these 1/2s are going to cancel out. Don't really care about those. The mass of A, that was the 150. And it was going at 4, so I've got 150 times 4 squared. B was the 100. It was moving the opposite direction at 5. When we square it, that's going to cancel out the negative, so energy being a scalar, direction doesn't matter. And that equals, oops, let's bring it a little bit bigger. That equals the 150 times I don't know squared plus 100 times the other I don't know squared. When we clean that up, I'm going to do a couple things at once. I don't like all these big numbers, so I would call that 3 and that 2. That's a 3, that's a 2. When I clean that up and multiply it out, 3 times 4 squared is 48. 2 times -5 squared is 50. And that's equal to 3 I don't know squared plus 2 other I don't know squared. And of course that means 98 equals 3 I don't know squared plus 2 other I don't know squared. That's my equation 2. Now we're done the physics of it. Now we're going to crank out and do a whole bunch of math. It's a system of equations. I've got an equation up here I called number 1 with a VB and a VA. I've got equation number 2 with a VA squared and a VB squared. 2 equations, 2 unknowns, I can solve them. Just because of that square, it's a little bit ugly. I'm going to sub 1 into 2. So I get 98 equals 3 VA prime squared plus 2 times VB was 1 minus 3 over 2 VA prime, and I got to square that whole thing. We got fractions, we got a square, we got a binomial, so lots of good stuff going on here. 98 equals 3, I don't know, squared, plus 2. Squaring a binomial means we square the first term. In this case, it's 1. Then we multiply the 2 terms together and double it. So I've got 1 times -3 over 2. Double that. That's going to turn into a -3. VA prime. And then square the last term, so it's going to flip it to positive 9 over 4 VA squared. Now I'm going to distribute the 2 into that bracket. So I get plus 2 minus 6, and then plus 9 over 2. Phew. Okay, now collecting like terms. I'm going to put it in what your math teacher would call standard form. I want a 0 on one side of the equal sign. I've got 3 VA prime squares here and 9 over 2 there. So a common denominator of 2. I got 6 over 2 plus 9 over 2, so we get 15 over 2 VA prime squared. There's only one group of VAs, that's the -6 VA prime. And then collecting like terms, I had a positive 2, but I'm flipping the 98 over, so I get -96. I don't like fractions, so I would multiply everything by 2. You don't have to. Most likely, if you're lucky, you're just going to throw this in a calculator or a website to solve it anyway. But for my brain, I would multiply by 2, and I get that. Everything there is divisible by 3. Again, we don't really have to if we're just going to ask a computer to solve it, but my simplest version of this equation in standard form looks like this. If you did it in kilograms, or if you did your algebra a little bit differently, by the time we get to this line here, we should all agree once we simplify in standard form or quadratic, we should all be getting that. I'm not going to try and solve that. I plugged it into my Chromebook, a website that can solve the quadratic. I got 2 solutions for VA prime. VA prime could be positive 4, or VA prime could be negative 3.2. They're both meters per second, of course. This is what's kind of cool about elastic collisions. In this great big monster solution, we asked the physics, when could this initial momentum balance between those 2 objects as the final momentum? When could this particular initial kinetic energy be split between the 2 as final kinetic energies? We did the math to solve it. And basically, the physics is saying there's 2 possible answers. The A ball could be moving 4, or it could be moving in the opposite direction at 3.2. If you look back at the question way back up here, the A ball moving 4, that was our initial condition. That's what we put into our very first conservation of momentum. So the physics doesn't really understand the context. When could these momentums and energies happen? Well, they could happen if the balls don't ever crash. If they don't collide in the first place, then A would just keep rolling at 4. That satisfies the momentum and the kinetic energy. This is our initial condition. And that's going to be an artifact of these elastic collisions. If you set it up right and do your math correctly, the initial condition is always going to be one of your solutions. It's as if the balls miss, or this is a solution before they crash. So we can ignore the plus 4. We'll carry the VA prime forward, the negative 3.2 forward. And just like whenever we're solving systems of equations, we're going to back sub. VB prime was 1 minus 3.2 times VA. The 3.2 happened to be negative 3.2, so we got some fractions and decimals there to work through. But doing the math, VB prime works out to be 5.8. If we had subbed the 4 into the VA prime equals 4 to solve for VB, we would have got VB's initial condition, which was the negative 5. Polishing this one off, our solution will be the 150 gram is moving at 3.2. Since we got a negative number that matches north in this case, flip back to the beginning, and the 100 gram is moving positive 5.8, which means south. That's the solution for this particular question. Moving forward, the fact that the initial condition is one of our solutions, we can use that as a step to help us solve the quadratic equation. So I'm going to kind of squish it in here. We knew that that's the quadratic equation we got, and I know that VA equals 4 is one of the answers. That means VA prime minus 4 is one of the roots. If VA minus 4 is one of the roots, then the binomial that'll make that work is I need to have a 5 up front, so that when I FOIL it, I get a 5 squared. And I need to have a positive number. 64 divided by 4, if I'm doing this right in my head, is 16. So since I know the initial conditions is one of the roots, I can kind of cheat. I don't have to do the quadratic formula. I know that VA prime equals 4 is an answer. I can use that in kind of some mental polynomial long division to figure out the other answer. So moving forward, I'm going to use this cool artifact that the initial condition is one of our answers to simplify the math in the last step and to kind of form a check. if I got to that simplified quadratic, and when I put a star beside, if when I solve it, the initial condition isn't one of my answers, then I've goofed up the algebra somewhere along there. The good news is we're not going to do two-dimensional elastic collisions. It just ramps up the math and doesn't really add any physics. And to be honest with you, if you did have a two-dimensional elastic collision, you would just throw it into a computer. There's lots of solutions or coding that have been done already, or you could do it yourself if you're really keen, but we'd just get it solved for us. No one really solves 2D